Bismillah ar-Rahman ar-Rahim. Welcome to tutorial number 4. And in question number 1, we have a large office building is supplied from 500 kilovolt transformer. The per unit impedance of the transformer is 5%. Okay, let me just bring the pen with this thickness. Okay, the transformer feeds nonlinear load with the bare phase harmonic spectrum of the total line current shows the fundamental is 100, the third harmonic up to the 9th. Assume that the fundamental current is 500 ampere. Determine the voltage magnitude of the following harmonic voltage developed at 480 volt due to harmonic current. Assume that the phase angle of the harmonic current are 0, and also he said neglect the short circuit impedance. Okay, and he give us the those parameters. Okay, so if we like to draw the equivalent circuit of the network, so we have a voltage source, and he said that neglect the source impedance, and then we have a transformer, right? And then we have the over here the load. So this is our nonlinear load over here. Okay, and he said that the voltage over here is 480 volt. We are given the impedance of the transformer in per unit, so we can find that one in ohm. So we need to find Z base on the voltage, on the low voltage side. We have S. Okay, so it will be V square 480 square over S, which is 500,000. So that will be Z base. Then we can calculate Z transformer in ohm. It will be Z per unit times Z base. So that will give us the transformer impedance in ohm. So this one again, this is the equivalent circuit for the network at the fundamental frequency. If we like now to draw the equivalent circuit for the network at the harmonic frequency, because this is what we need to find. So the this one will be shorted out, the generator will be out. So what we have only transformer impedance, and then it is fed from a harmonic source. Okay, so this is the harmonic source. That is the transformer impedance, which will be Z time H, right? Because it is mainly inductive. Okay, so to calculate the voltage, we need to find the impedance, and then you multiply it by the third harmonic current, 5th, 7th, 9th, and that will give us the different harmonic bus voltage, and then we can calculate the total harmonic distortion for the voltage. Okay, so this is the fundamental current, the third 70%, and so on. The transformer, the Z base of the transformer impedance at fundamental frequency. Then if we calculate the voltage due to the third harmonic, So again, what we need to do, this one will be our equivalent circuit. Okay, so we need to find the third harmonic current is with us. We need just multiply the third harmonic current by the transformer impedance times 3, so that should give us the value of the voltage for the third harmonic, and we can do the same thing for the rest of the harmonic, for the fifth and for the seventh and ninth. Okay. So this is the third harmonic voltage. So it is the third harmonic current times the transformer impedance at fundamental time 3. Okay, because we are now finding the third one. Then time port 3 to find the line voltage, and that will be the total result. So now if we like to find what will be the total harmonic distortion, we take the square root of those value square divided by V1, and that should give us the total harmonic distortion, and it will be 20%. Okay, so that with respect to the first problem. Now let us move to the second one. It says that harmonic current spectrum of a rectifier connected to three-phase 34.5 kilovolt 50 Hertz feeder is given below. So those are the harmonic current. So this is the fundamental component will be 100 ampere, the fifth harmonic will be 20.2, and so on. A star connected inductive load. So this is the load that we have. We have inductive load that take 300 with minus 20 ampere, and then we have also a star connected capacitance, which is used to improve the power factor to 0.98. is also connected. Okay, so again we have a rectifier, we have a load, inductive load, and we have a capacitor bank. And then he say that the 34.5 bus bar are fed from transformer, from 25 megavolt transformer, and this transformer will have this equivalent impedance per unit, and the short circuit impedance for the system is 0.0125. Okay, what is the question? What the question is, he said, sketch the diagram of the system, calculate the value of the capacitance. So we need to calculate the capacitance that will be connected, and determine also the harmonic current and the voltage. So again, we need to do the calculation for the harmonic current and voltage, okay, for different branch current, and then we need to calculate the total harmonic distortion for bus voltage and for branch current, and also we need to determine the critical harmonic. So what is the critical harmonic? It is actually, it will be the largest harmonic. I mean the harmonic that will give a large current. So that will be the critical one. Okay, so let us do it step by step. First of all, we need to find what will be the value of the capacitor bank that will be connected. Okay, so this is our first step, is to find the capacitor bank, and the value of the capacitor bank that will improve the power factor to 0.98. Okay, so what is our circuit to find the capacitor bank? We have a voltage source with a source impedance, then we have a transformer, and over here we have two load. We have a rectifier and we have inductive load. So this is without the capacitor bank. Okay, because to find the capacitor bank, we need to find what will be the power factor of the system. So initially, this one takes a current of 300 with angle minus 20, and this one and the rectifier take a current of 100 ampere with angle 0. Nothing given about the phase angle, so we can take it as 0. Okay, so this one will be the different current. Okay, the voltage of the bus bar, he told us also that, or of the feeder, the voltage of the feeder will be 34.5. Okay, so the voltage over here is 34.5. So this one will be, I can say, the rated voltage of the feeder. So from here, what we can do, we can calculate the real power and the reactive power taken by the system over here. Again, why we need to do that? We need to do that in order to calculate what will be the capacitor bank, because in order to find the capacitor bank that will be connected in the system, we need to do the following. So this is the real power taken by the system. Okay, this one will be the reactive power taken by the system. That will be S. Okay, and now, so this is P, and from there to there will be, I will call it Q1. Now he told us that we're gonna connect capacitor bank, and that capacitor bank will improve the power factor. So this one will be theta 2. Of course, that one will be theta 1. Okay, this one will be theta 1. So that one is all angle, that one will be theta 1. So and now we're saying that now we are saying that the capacitor bank will provide this much of Q, and now our new Q will be this one. So this one will be now our new Q. Okay, so in order to find QC, which is this one, we need to find Q1, right? And this one will be our Q total for the system. Okay, so we know that in order to find this angle theta 1, in order to find theta 1, we need to find P and Q. P and Q, so that will give us theta 1. And then if we subtract QT from Q1, that should give us QC. Okay, so now how to find P? How to find P for this system? So P will be equal to IB cosine, right? So it will be this current time the voltage cosine the angle. So it will be, if I call this one I1, I call this one I2, so it will be I1 V cosine theta 1, cosine, I mean the angle between the voltage and the current, which is 0, plus I2 V cosine the angle between the voltage and the current, which is 20. So this one will be 0, okay? This angle will be 0. So that will give us P. And then we can find also Q, I1 V sine 0 plus I2 V sine 20. So that will give us a Q. Okay. And now he told us this angle, so this angle is given to us, right? That angle is given to us. So we can calculate QC will be given as Q1 minus Q. So QC will be given as Q1 minus QT. And what is Q? It is P tan delta, P tan theta, right? That tan is equal to Q over P. So Q, okay, so tan is equal to Q over P. So Q will be equal to P tan. So QC will be P open bracket, because it will be the same P tan theta 1 minus tan theta 2. So it will be equal to P tan theta 1 minus tan theta 2. So that will be QC. So once we find QC, we can find the value of XC, because XC will be equal to V square over QC. So we can find the value of the capacitance. Okay, so this is the first step that we need to do. We need to find what will be the value of the of XC. So to find the value of XC, again we need to find theta 1. To find theta 1, we need to find P1, Q1. So once we find P1, Q1, so then we're able to find the value of QC. Okay. Okay, so again, so this is the circuit without the capacitor, so the total P will be equal to P over there plus P over there, as it is written over here. Okay, so we find P, we find Q, okay, then we can find theta old, which is tan inverse of Q over P. Theta new is given. Then we can find QC. From QC we can find XC. From XC we can find the value of C. Okay. So this process is done, and only to find the value of XC. Okay, we have to find the value of XC. Of course, also we need to find the also the rest of the impedance. So for example, for the source impedance, it is given to us in per unit. So we need to convert that one to ohm. We multiply it by the Z base, and Z base will be at that base voltage. Okay, and to find also the source impedance at any harmonic, so it is only reactance, so multiplied by H. We need to do the same thing with the transformer. So R plus J omega L per unit multiplied by the base, that will give us the impedance in ohm. And now for the H harmonic, so the omega L, so over here H will be multiplied by the by XL. Okay. To find also the load impedance, because we have a load that will consume 300 ampere with angle of -20, so we need to divide we need to take the voltage, divide that one by the current, so that will give us the load impedance at fundamental frequency. To find it at any harmonic, we need to multiply it by H. Okay, so now the all system parameters are given to us, including the capacitor bank. Okay, so now this one will be our equivalent circuit for the harmonic frequency. So we have the harmonic source, we have the Z load, we have the impedance of the load, we have the impedance of the capacitor, and then we have both the transformer impedance and the system voltage source impedance connected in series. And then we can now do the calculation straightforward. So to find this voltage, we need to find those three impedance. We need to connect them in parallel. Let us say at the third harmonic, we multiply it by the third harmonic. That will give us the voltage. Then to find the current, voltage divided by Z load, voltage divided by ZC, voltage divided by this total impedance. To find this voltage over here, the voltage at node A, we need to multiply this, the source current at, for example, for the third harmonic times Z source for the third harmonic, so that will give us the voltage at bus A for the third harmonic. Okay, so that will be the calculation. Okay, so we find the total, we find P, the voltage at node B for the third harmonic. We divide the voltage over each impedance. That will give us the current. We multiply the current time the source impedance to find the voltage at the source, or at A, at node A. Multiply that one by √3, and of course we need to refer to the high voltage side. And then of course we are repeating the process again with the other harmonic. This is only this is only for the fifth harmonic, but we need to do it for 7th up to 47th harmonic. If we look at the so this is given, the harmonic current are given to us, and now the load current for different harmonic is calculated, the source current for different harmonic are calculated, the capacitor current for the different harmonic are also are found, and then we can calculate the voltage at node B, the voltage at node A, and then we refer to the high voltage side. Now if we look at those value of the current, we will notice that at harmonic 7, at the 17th harmonic, look at the current, look at the source current, look at the current with the capacitor bank. They are really shooting up. For the fifth 19, it is jumped to 49. This is for the fifth, it is 2, but this one jumped to 62. So this is the most severe harmonic, which is 17, followed by 13th, and then 19th harmonic. Okay, thank you. That's all for this